enthalpies of formation is one of the last final ways you can find the heat of a reaction. So you have enthalpies of all kinds of things. Heat of vaporization, enthalpy of vaporization, turning a liquid to a gas. Heat of fusion or enthalpy of fusion, which is melting solid to liquid. You have enthalpy of combustion, which is associated with burning in the presence of oxygen. So you have heat of anything. Enthalpy of acid-base reactions, enthalpy of any process that's occurring. But for enthalpy of formation, it's a very specific. So the symbol is delta H with a sub F and usually a little standard 0. This means standard states. So enthalpy of formation is the formation of a compound from its constituent elements in their standard states. So it's the energy that is released in forming a compound from its elements in their standard state. The standard states of elements are 298 Kelvin and 1 atmosphere. All of these values are published in any chemistry textbook. So if you look, the heat of formation values, so here you're looking at barium sulfate. So to make a mole of the compound barium sulfate from its elements, barium, sulfur, and oxygen would release 1,465 kilojoules for every mole that you made. Notice an element has a heat of formation of 0 because you cannot make an element from its elements. Almost all of your heats of formation are negative values because to make an element, to make a compound from its elements will release energy. So heat of formation is a specific reaction where you have a mole of compound made from its constituent elements. So if we look at these, this is just to remind you of what those standard element conditions would be. So hydrogen standard state is a gas, okay, so H2 gas. Lithium is a solid. Carbon standard state is graphite. Nitrogen is a gas. Oxygen, these are diatomic standard states. Gases, sodium is a solid. Water standard state is a liquid. Carbon dioxide gas. Hydrogen chloride is a gas. Methane is a gas. Methanol up here, standard state is a liquid. Benzene is also a liquid, and sucrose is a solid. So you want to make sure you're in the standard state. 298 is 25 degrees Celsius. So that is pretty much the standard state that you would see on the periodic table. That is the state of matter that we're looking for. So by definition, the standard state of an element has to be 0 because you cannot make an element from an element. So each of the following substances in these questions we're asking you to write a standard enthalpy of formation equation. So here's how you want to do that. We want to make sodium oxide. So make sodium oxide on the right-hand side. There's its formula. There's its standard state. From its elements, it would be sodium and O2. You can only make 1 mole. So when you balance this equation, you can't put a coefficient in front of the sodium oxide. You need to, you've got your 2 sodiums, but you need to cut your oxygen coefficient by 1/2. So 1/2 O2 gives you 1 O. So the equation needs to be balanced, and it needs to be formed from its elements. Look at the next one. You've got potassium chloride, so that's what you're looking to make, and you would be making it from potassium and chlorine. Chlorine in its standard state is a gas, diatomic, so to get the equation to balance, you need 1/2 Cl2. Going down to glucose, you have a more complicated formula, so C6H12O6, so you would need, in its elements, to make this heat of formation, 6 carbons, graphite, 6 hydrogens to give you your 12 hydrogens. So your diatomic hydrogen is your standard state. So you need 6 of those and 3 O2s. So you need to make sure you are using only elements on the left-hand side to make a mole of that compound. There's your iron 3 bromide. So we'll practice some of these in class. But make your product first with the correct formula and state, and then just break it apart into its elements. So to get 3-bromine, you need 3½ Br2. What's nice about heats of formation is that you can find the heat of a reaction by taking the sum of the heats of formation of the products and subtracting the sum of the heats of formation of products minus the heats of formation of reactants. That is important. It is always products minus reactants. So if you look at the logic of this, okay, when you form products, that is going to release energy. When you break apart reactants, that's going to require energy. All of your heats of formation are tabulated, okay, as if they are exothermic. They are making that compound from its elements. So therefore, you need to have products minus reactants to give you the correct sign for exo and endothermic. Okay? If you get back more energy when you make them than it takes to break them, that's what's going to give you this negative delta H. So you always have to look up these tabulated values. So let's look at an example. If I looked up the C3H8 heat of formation in the book, and I think I can find that pretty quickly. So C3H, make this a little bigger. Can't do that when I'm making a video. C3H8 right there is negative 104 kilojoules. Now some books have different values than others. Okay. So there's I have a more precise book that I used this. So I've got remember it's going to be your products minus your reactants. So you're going to look up your values, and you've got 3 of your carbon dioxides right here. There's your carbon dioxide value, plus 4 of your water heats of formation, minus your C3H8, okay, plus your 5, 0. And it's nice to put the 0 in there. So the sum of the heats of formation of the products minus the reactants gives you the heat of the reaction. So as long as you have put your correct thermosigns in, remember this negative is to change your reactants, so you've got your products minus reactants, so your reactants are going to be endothermic processes, so that negative sign is actually to change these thermodynamic signs so that they'll come out with the correct reaction sign. We'll look at one more, and the rest of these we'll do in class. So you have to look these up in your book. You have a textbook. It has the values. They may differ from mine depending on which book we use, but it's products minus reactants, so there's the 6 CO2. Obviously, the CO2 value isn't going to change, plus the 3 times the H2O in the liquid state, so you have to look up the liquid state, minus the 49.0, which would be for your C6H6, and then your 7.5 times your 0. So it's just a matter of plugging the numbers in with the correct signs. So this is a very easy way to find that final delta H, but you can only use it if you've been given an equation and the tabulated data. So often in lab, to decide if your reaction value is correct, you use your tabulated data from your textbook, which is always available and has most of your compounds, and you do heats of formation to solve for what the delta H would be. The delta H, if you found this in the calorimeter, is going to differ because that's an experimental result. So we will work more of these problems in class, but this is one of the simplest, easiest ways, if you're given this information, to find delta H.